So friends, today we are beginning a new chapter, multiple linear regression. Here we will try to cover what is multiple linear regression, how it is executed, what are the steps, what are the assumptions that have to be satisfied for a multiple linear regression to be valid, how they are tested for, and if there is found to be some misalignment, what are the corrective measures that can be taken. So all these things we will try to understand in this chapter. So friends, let us first get a clear idea of what multiple linear regression is by comparing it with simple linear regression. So let's say we have an equation y is equal to a0 plus a1x1. Now friends, this has two characteristics. One is it's a linear relationship. x1 is linearly related to y, and the second thing is there is only one variable, one independent variable. Now these two conditions when satisfied, we call this equation a simple linear regression. That is, we have a dependent variable and we have only one independent variable and we have a linear relationship between them. This is what is a simple linear regression. So friends, naturally, when the number of independent variables increases from 1, it becomes what we call a multiple linear regression. So when y, let's say, is equal to a0 plus a1x1, a2x2, a3x3, a4x2, a5x5, then this kind of an equation doesn't need to be 5, only if it is more than 1, that is the independent variables, the number of independent variables. If it is only more than 1, this is called a multiple linear regression. So this is the basic difference between what we call a simple linear regression and what we call a multiple linear regression. So in case of a multiple linear regression, the two conditions that are being satisfied are y is the dependent variable and x1, x2, x3, x4, these are the independent variables. The characteristic is they are maintaining a linear relationship with the dependent variable, right? Linear relationship. This is being maintained in between the dependent and the independent variables. The second condition is the number of independent variables is more than 1. These two conditions when satisfied, we call this multiple linear regression. Now, let's try to understand multiple linear regression with the help of an example, friends. So the example goes like this. Our assumption is the price to earnings ratio of a stock is dependent on the stock's earnings growth rate and debt to equity ratio, right? So the price to earnings ratio of a stock is dependent on the stock's earnings growth rate, EGR, and debt to equity, that is DE ratio. Now these relations, we also assume that these relations are linear, right? The relations are linear. So the equation is like this. Let's say PE is equal to 5.1 plus 57.6 multiplied by EGR minus 31.8 multiplied by debt to equity ratio. So this is our equation, friends. Now we need to find out the PE ratio of a stock whose earnings growth rate is 40% and DE ratio is 0.25. Earnings growth rate is 40% and DE ratio is 0.25. Now what is the PE ratio? This is what we need to find out, right? So the method is very easy, friends. We just plug in the values here. PE is equal to 5.1 plus 57.6 multiplied by 0.4, which is the EGR, that is the earnings growth rate, minus 31.8 multiplied by 0.25, which is the debt to equity ratio, or DE. Now we easily calculate the values, friends. 5.1 plus 57.6 into 0.4. This is 23.04 minus 31.8 into 0.25. 31.8 into 0.25. This is 7.95. Now the value comes to be 5.1 plus 23.04 minus 7.95. This is equal to 20.19. This is our required PE ratio, friends. Now this is an example of a multiple linear regression. Why? Because the dependent variable, which is PE, is dependent on two independent variables, that is more than one independent variables. Earnings growth rate and debt to equity ratio. Now friends, we need to be very careful when interpreting these numbers, that is plus 57.6, minus 31.8 and 5.1, that is plus 5.1. So what do they mean? Let's try to understand. Let's start with plus 57.6. What does this mean? This simply means keeping DE ratio, that is debt to equity ratio, constant. 1 unit increase in EGR leads to 57.6 units of increase in the PE ratio. So keeping DE constant, 1 unit increase in EGR leads to 57.6 units of increase in the PE ratio. Similarly, keeping DE constant, 1 unit decrease in EGR shall lead to 57 units of decrease in the PE ratio. So this plus sign indicates that if one increases, the other will also increase. And how much will it increase? By the multiple of this number, coefficient, right? Similarly, what does this 31 minus 31.8 mean? This simply means keeping EGR constant, keeping earnings growth rate constant, 1 unit increase in the DE ratio leads to 31.8 units of decrease in the PE ratio. So this time the relationship is opposite. This minus sign is ensuring that. So let us write it. So keeping EGR constant, 1 unit of increase in DE ratio leads to 31.8 units of decrease in the PE ratio. So increase of one leads to decrease of the other. Similarly, 1 unit of decrease in DE ratio will lead to 31.8 units of increase in PE ratio. So this time the relationship is inversed. Now what does this 5.1 mean? This means that when earnings growth rate is 0 and debt to equity ratio is 0, then the PE ratio generally tends to be 5.1. So the third point we can write here. So when EGR is 0 and DE is also 0, PE tends to be equal to 5.1. Now we have certain terms that we use for these coefficients, that is 57.6, 31.8, and also we have a separate term for this 5.1. This 57.6 and 31.8, these are called partial regression coefficients. Why are they called partial regression coefficients, friends? Because for PE to be explained by any one of them, the other one needs to be kept constant. So for PE to be explained by EGR, we have to keep DE constant. For PE to be explained by DE, we need to keep EGR constant. When you want to explain PE with any one of them, we have to make the other one constant. If there were 10 variables like this, like EGR, DE, and there are other variables also like ROE and PB and etc., then if we are trying to explain EGR and 57.6 with respect to PE, then all other factors have to be kept constant. So this has partial explanatory power. So this is called partial regression coefficient. Similarly, if we want to explain PE with respect to debt to equity ratio, we have to keep others constant. They cannot change. Then only this coefficient can define PE ratio. So this has partial significance. All of these together tend to explain P ratio very well. But individually, they are only partially explaining it. So we call them partial regression coefficients. This 5.1 is called the intercept. When the other values turn to 0, P ratio remains or tends to remain about 5.1. So this is the intercept. So if you try to draw a diagram of this, let's try to draw a diagram. It will be a 3D diagram, right? Like this. Let's say this side it is EGR. This side it is debt to equity. And the vertical line represents the PE ratio. So if we draw a line at 0 EGR and 0 DE, PE is somewhere here. And then the line moves like this. Like the shadow of this line can fall somewhere like this. So this is a 3D way of explaining this equation. But if the number of variables increase to 3, 4, 5, 6, 10, 100, then picturization is not possible, because beyond 3D we are not able to picturize, right, or visualize. Then only the statistics and mathematics will work. So this is an introduction of the multiple linear regression. Now we will proceed into the assumptions behind the multiple linear regression. What are the assumptions that hold the multiple linear regression as valid? We will try to understand that. Now we come to the assumptions behind multiple linear regression. Any multiple linear regression has to align with these assumptions. If these assumptions are found to be violated, the linear regression or the multiple linear regression can be counted as invalid. So it is very important we understand the meaning of these assumptions, how to test for these assumptions, and how to correct, if possible, the violations that happen. So let's get on with it, friends. So first we come to linearity. What is the meaning of this, friends? Linearity. The independent and dependent variables are linearly related. So this simply means that the dependent variable y has a linear relationship with the independent variables in which it is dependent upon, right? So this is like a0 plus a1x1 plus a2x2 plus a3x3, assuming in this example y is dependent upon x1, x2 and x3. This is what we call a linear relationship. Now what is a non-linear relationship, friends? Let's say if y was like this, y is equal to e to the power a0 plus a1x1 plus a2x2 plus dot dot dot. This is not a linear relationship, friends. This is an exponential relationship. Again, if y can be said it is equal to a0 plus a1x1 square plus a2x2 cube plus dot dot dot. This is again not a linear relationship. These two are not a relationship which is called linear. A linear relationship is like this. Now what is the difference? Clearly we can see, friends, here the variables are raised to the power of 1. x1 basically means x1 to the power of 1. x2 basically means x2 to the power of 1. Here we can, in the polynomial example, in the second example, we can see x1 square, x2 cube. So this violates the linear relationship. Here y is equal to exponential to the power of a0 plus a1 x1 plus a2 x. So this is again not a linear relationship. This is an exponential relationship. The relationship which can be called linear is like this. Every variable or independent variable is raised only to the power of 1, and there are coefficients which are real numbers. So this is how linearity can be defined. The second one is homoscedasticity. So how is homoscedasticity defined, friends? The definition is the variance of the regression residuals does not shift across observations. So let's look at it by an example here. Let's say there is one data which looks like this. Right, friends? Now here we can draw a regression line, a linear regression line. We can clearly see this is a linear regression. So we can draw a line. So we can draw a regression line like this, friends. Here you can see across the different observations. If you take this portion of the observations, if you take this portion or this portion or this one, you will see that the variance, that is the regression line with respect to the points and their spread, is quite uniform. This region here is not different from this region, which is again not very different from this region. So that is how the data is distributed. This is called a data which is aligned with homoscedasticity. That is, the variance of the errors are not drastically different across the observation zones or the regions. Now we look at a different data, friends. Let's say we have a data like this. You can see the data is a different kind of a data. If you divide the data in two zones, let's say, in the first zone and the second zone. Now you can see the variance is clearly different in the two zones, right? As the observations are increasing, then parallelly the variance of the residuals is also going up. So this is a data which violates the condition of homoscedasticity. This is a data which can be called heteroscedastic. Independence of errors. The individual observations are independent of one another. This implies the regression residuals are uncorrelated for all observations. So what do we mean by this? What do we mean by independence of errors, friends? So let's say there is a data where the first observation is here, the second observation is here, the third observation is here, the fourth is here, the fifth is here, the sixth is here, the seventh is here, the eighth is here, ninth, 10th. Like this the data is, right? Now if you draw a regression line, so the regression line is not very perfect, but we can try to explain from here only. You can see if the first error is positive, that implies the second error will be negative. And if the second error is negative, that implies the third one will be positive. If the third one is positive, that means the fourth one is negative. So this is a relationship being established between errors. The first error is basically deciding what the next error is going to be. The second error is basically deciding what the third error is going to be. So this means the errors are not independent of each other. They are not random kind of a thing. They are basically having correlations with each other. So this is what we mean by independence of errors. Another example can be, let me take another example. Let's say there is a data where the first data point is 1, right? The second data point is 1. The third one is 2. The fourth one is 3. The fifth one is 5. Now this is basically a Fibonacci data set. So here if you try to draw a regression line, what will happen is the errors will follow a definite pattern. The previous error will actually decide what the next error is going to be, because here the data points are itself dependent on their previous values. So basically here y2 is equal to y1 plus y0, or yn is equal to yn minus 1 plus yn minus 2. So basically the two numbers previous to it the addition of it results in the third number. 1 plus 2 again decides in 3. 2 plus 3 decides again it is going to be 5. 3 plus 5 decides it is going to be 8. 5 plus 8, 13. This is how this series goes on. If you try to regress linearly this kind of a data, what will happen is the errors will be correlated with each other. So this is going to be another example of non-independence of errors. This is going to be a violation. And what do we mean by independence of errors? Obviously, this is a kind of a data which represents that. Here the data are pretty randomly distributed. You cannot find a pattern in them that they are having the previous error is having a value which is influencing the next error. That is not the pattern that is there, right? Now we move on to the next assumption, which is normality. What is meant by normality, friends? Normality means that the errors are in the pattern of a bell curve. Let me show you how. Now let's say you want to plot the frequency of the errors. That is, what value range of errors occur how many times. So you draw a graph like this. Here you write 0 and here you write -1, -2, -3, like that. Here you write +1, +2, +3, like that. Okay. Now you want to plot the frequency. Now you find that most of the errors lie in this area between -1 and +1, and most of it is very near to 0. In case of a linear regression, this is what you will find, that most of the errors are near to 0. And then as you move to higher values, the frequency comes down, right? You are going to extreme negative values here and the frequency is coming down. If you go to extreme positive values also, you will find that it is coming down. So the shape of this will be like a bell curve. This will be like a bell curve. This pattern is basically called a normal curve. This pattern is basically called a normal curve. As the extreme values come, the frequency of them go down. The frequency is found where? This is basically the frequency. This vertical axis is basically what the frequency is denoting. And these are the values. These are the error values. These are the negative error values. These are the positive error values. So as the value of the error is going to the extremities, their frequency is coming down. So this is how the error is distributed. We call it normality of the errors. Next we go to the next assumption, which is independence of independent variables. So what do we mean by that? There are two aspects to it. Independent variables are not random. Second aspect is no exact linear relationship exists between two or more of the independent variables or their combinations. So what do we mean by this? Let's try to understand it, friends. Independence of independent variables. What do we mean by this? Firstly, independent variables are not random. What we mean by this? Basically, friends, the example that we took, PE, it was dependent on EGR, that is earnings growth rate, and debt to equity ratio, right? Now these factors, EGR and debt to equity ratio, were not just picked like a lottery. They were not randomly picked. Somebody had a fundamental logic behind it. There was an assumption and it was checked to be valid according to this hypothetical example. They were specifically chosen for definite reasons, that they will be influencing the variable that we want to deduce. So we picked them. They were not randomly picked. So they are not random. That is the first aspect of it, right? Now we come to the second aspect. The second aspect is EGR has no linear relation with DE, right? EGR has no linear relationship with DE. This assumption has to be abided by for this multiple linear regression to be called as valid, right? Y is equal to A0 plus A1x1 plus A2x2 plus A3x3. Here, there can be no linear relationship between x1 and x2 or x2 and x3 or x1 and x3 or x1 and combination of x2 and x3 or x2 and combination of x1 and x3. This is not allowed. This is not allowed. That is, there can be no linear relationship or no linear correlation between them. x3 cannot be linearly correlated between x2 and x1 combination also, right? And individually, as we just said, x1 cannot be linearly related to x2. x2 cannot be linearly related to x3. Similarly, x1 must have no linear relationship with x3. These assumptions have to be satisfied for this multiple linear regression with this equation to be validated, to be called as valid. So this is what we mean by independence of independent variables. Firstly, they are not picked randomly. There is a reason they are being picked for. Secondly, between them there is no linear relationship. There is no correlation between either of them individually or in combinations. There is no such possibility. This assumption has to be valid, or this assumption has to be abided by for the multiple linear regression to be called as valid. So this was the last or the fifth assumption and the last assumption that we discussed about. Now we will come to how to check for the possible violations of these assumptions. Let's get into that. So friends, we will now look at the different measures of goodness of fit, and this will be pertaining to multiple linear regressions. So we will start with the simple ones, then go on to more complex ones. So how well a regression, linear regression, multiple linear regression or simple linear regression is fitting the data, There are various metrics to measure that. The most popular among them is arguably the R squared. Now, what is the way to measure this R squared? Let's discuss that. Let's say y is linearly dependent on x1 and x2, two variables, right? Therefore, the regression equation can be stated like this: a0, a1 x1, a2 x2. Now, this portion is basically the predictive part. This predicts a single value of y, but this may not be the exact value of y. Like we saw in the data here, friends, the line, let us visit this. Here there is a line, right? This line is trying to be the best representation of these data points, right? But these data points are not exactly all on this line. There are some of them are upward, some of them are downward. So there is some noise here. Now this noise has to be represented by something called the error. So that's what we do right now. So because we are talking about the exact value y, we add something called the error here. So this basically represents the noise that is there in the data points. This portion, this a0, a1 x1, a2 x2, this is the line. But when you add the error with this, the data set becomes complete. Okay. Now, let's say there are 1000 data points. 1000 data points means, let's say you have an Excel sheet where there are 1000 sets of value. So there is value set 1, where there is an x1 value given, an x2 value given, and a y value is given. There is row number 2, where another x1 value is given, another x2 value is given, another different y value is given. There is row number 3, where there is another different x1, another different x2, another different y value is given, right? Like this, there are 1000 data points in this sheet, where there are 1000 sets of x1, x2 and y values given. Now, we have already said that without the noise part, what we are getting is the exact regression line. So let's say the data point looks like this, the data set looks like this. So we have x1, we have x2, and we have the actual y values. And when we plot it, the 3D version looks something like this, let's say. This is basically, I'm trying to represent a 3D representation here. So these are the point plots. And this is not an exact line, but this is linear in nature. Now we can draw a linear regression line here. So let's say this is the regression line. This is basically what we call the y hat line. The set of all the y hats. What are these y hats? Friends, basically this is y hat is basically the predicted y without the noise. So y hat is exactly a0, a1 x1, a2 x2. It is a single line. There is no noise about it. The data points actual y's are creating some noise, but the predicted one is a single value. there is no noisiness about it. So this is what y hat is. But the actual values are not exactly matching with the y hat, right? Some are above, some are below, right? So when you try to measure y predicted, there will be some error in each of these values. So what is the error? This error is nothing but y minus y hat. So for each of these examples, we can measure y minus y hat, right? We can have 1000 sets of y minus y hats. Set number 1, y minus y hat from row number 1, let's say. Set number 2, y minus y hat from row number 2, let's say. Like this, set number 3 from row 3, y minus y hat. This we do for all the 1000 values. All the 1000 values. So we might as well write them as y1, y2, y3, y1000 and y hat 1, y hat 2, y hat 3 up till y hat 1000, right? Now what we do is we square each of them. Square each of them. And we sum them up. Now why do we square and sum? The reason is, if you see, in a proper multiple linear regression or in a proper linear regression for that matter, because the errors are normally distributed, what you will have is the values will cancel out. If you look at this data set, friends, you can understand that the errors below and above are equally distributed, both in terms of frequency and magnitude. What I am trying to say is, if you plot the frequency of different values of errors, the higher values of errors which are negative are almost equal to the positive higher values of errors. The medium values of errors are again balancing with the medium values of positive errors. That is, the medium value negative errors balance out with medium value negative errors. Again, the low value errors which are negative balance with the low value positive errors. Low value means near to 0. High means far away from 0. Far away from 0. Medium means in between these two extreme values. Almost 0 and far away from 0. These are in between them. Medium errors. They will cancel out because negative and positives are balancing each other. So what we do is we square them up. When we square them, all the values become positive and we can have a measure of the error. So we square them and we sum them. This sum, we call it sum of squared errors. Now, previously we were trying to measure something called R squared, right? R squared we were trying to measure. Now, R squared, to measure it, this SSE, sum of squared error, is a very important part of it. But we need another piece to solve this. How do we get that another piece? Let's try to understand. So first off, what we do is we take the average of all these y values, right? All these actual y values, we take the average of it, and let's say we call it y bar or y mean. Then what we do is we subtract this average value from all the 1000 actual y values, one after the other. From y1 we subtract the average value, from y2 we subtract the average value, from y3, these are all actual values, right? We subtract the average value, and we do this for all the 1000 cases, all the 1000 instances that we have, and we square them. And likewise, after squaring is done, we sum them up. This sum, we call it sum of squared total. Sum of squared total. When we divide sum of squared error by sum of squared total, we get a measure of a proportion of error which is there in this data set or in this regression data set, right? proportion of error or percentage of error, you can say. A measure of the percentage of error or proportion of error, you can say. So therefore, the percentage of accuracy will be what? It will be 1 minus this. This is the ratio of the error. 1 minus this will be the ratio of the accuracy or the precision, right? And this measure is what we call as R squared, denoted by small r also, like previous. So this is the value. Now, if we simplify it further, this becomes SST minus SSE whole divided by SST, sum of squared total, right? This can be written as sum of squared regression by sum of squared total. So R squared is equal to 1 minus SSE by SST, or directly SSR by SST. SSR is nothing but SST minus SSE. Okay. So let me write the equation separately. Now in simple linear regression, this would have been fine. But there is a problem here, friends. The problem is, in case there are multiple variables being added, we do not know which one is more significant, which one is less significant, which one is not significant at all. Just adding something may not make sense, or it may increase the R square but may not mean anything actually. So how do we resolve that? For this problem, we have something called the adjusted R squared. This basically takes into account the number of features that are being added, and it eliminates the impact or the apparent impact, which is not an actual impact of the added variables, right? Now, how do we deduce the expression for it? We start with R squared only and deduce it step by step from there. Now R squared is equal to, we can write it as 1 minus R squared, right? You see, if you open up the bracket, it becomes R squared. Now in the second part of this expression, we incorporate the impact of the number of features for a multiple linear regression. How do we do that? What we do is, we write 1 minus n minus 1 by n minus k minus 1 multiplied by 1 minus R squared. This is the factor that we add in the R squared expression. So what is this n and what is this k? So n is the number of samples, which means, statistically speaking, n minus 1 is the degree of freedom and k is the number of features or number of independent variables. Number of independent variables like x1, x2, x3, all this. Now how does it impact the R square, actual R square value? What happens is, as the k increases, this expression increases, right? This expression increases. And as this expression increases, this whole expression, n minus 1 by n minus k minus 1 multiplied by 1 minus R square, this whole expression goes up. And as this goes up, 1 minus a higher value obviously reduces the initial value. If k was 0, there was no value of k. This value is equivalent to R square. We are not taking into account the number of features. The moment we introduce k into it, what happens is, this value, this portion of the value goes up. And when this part goes up, 1 minus a higher value, obviously this value comes down, right? So that is how it adjusts the actual R square, or adjusts the simple R square to an adjusted value of R squared, which gives a better expression how the number of variables or the increasing number of variables is impacting the R squared. So it gives a more accurate value. Now in our example, where there are 1000 data sets, right? We say there are 1000 data sets. In this example, let's say the R squared was 0.82. or about 82%, right? And the equation had two variables, that is k was equal to 2 and n was equal to 1000. Therefore, adjusted r squared we can calculate as 1 minus 1000 minus 1 by 1000 minus 2 minus 1 multiplied by 1 minus 0.82, right? Now if we calculate this, friends, this comes to 999 divided by 997. This is 1 minus 1.002006 and 1 minus 0.82, 1 minus 0.82 is 0.18, 0.18. This translates to 1 minus 0.180361. This is equal to 0.81964 or 9639 to be precise. So you can see, compared to this, there is a little bit of a decline, and the more the number of k is, more the value of k is, more will be the impact, right? So that's how adjusted r squared works. Now, does it always reduce the r squared? The answer is no. There is a catch to it. Now, the adjusted r squared is basically denoted by r squared with a bar above it, right? R squared with a bar above it. Now, an important point we have to notice, here we saw that the r squared or the adjusted r squared reduced, right? But does it always reduce in value? The answer is no, there is a catch to it. So let's understand what that is. When the t statistic is greater than 1 in magnitude, at that situation, addition of a new variable results in increase of adjusted r squared. The opposite happens when the magnitude is less than 1. That is, when the t statistic is less than 1 in magnitude, addition of a new variable results in decrease of adjusted r squared. So this is basically the caveat. A key's information criterion. This is named after its inventor, a statistician named Akiki. Now, this criterion, now what is the measurement method for it? So Akiki's information criterion, or AIC, is measured like this: n into natural log of sum of squared error by n plus 2 into k plus 1. Here n is the sample size, k is the number of independent variables, sum of squared error SSE, and ln is obviously natural log. So this is the expression: n into natural log of the ratio between sum of squared error and number of samples plus 2 multiplied by k plus 1. The lower this value, the better it is. And this criterion is generally minimized when the purpose of the regression is predictive. So when you are trying to predict something through a regression, you should look at minimizing AIC. There is another metric called Schwarz-Bayesian information criterion. Let's look at the expression for that. Schwarz-Bayesian information criterion. Let's look at the expression for this, friends. So the BIC, or the Schwarz-Bayesian information criterion, is given by n multiplied by natural log of the ratio of sum of squared error by n plus natural log of n multiplied by k plus 1, which is the number of variables plus 1. Now, this number tends to be greater than AIC generally, because here in AIC, instead of log of n, we have a 2. But for even the smaller values of n, ln tends to be greater than 2, even for small samples. So that's why BIC tends to be greater than AIC. But when is BIC used? We said AIC has to be used when you are using a regression for predictive purposes. When is BIC used? BIC is used more when you are trying to judge goodness of fit. So let's say you have two equations, two multiple linear regression equations. One is y is equal to a0 plus a1x1 plus a2x2. And you have another expression which is y is equal to a0 plus a1x1 plus a2x2 plus a3x3. Just for example, we are taking these two. Different models are there. So which one is a better fit? If you have to decide, you should look at BIC, Schwarz-Bayesian Information Criterion. And which one has a more predictive power? If you have to answer that question, you have to look at their AIC. That is how you choose which metric to be minimized. Now let's say this is model 1 and this is model 2, right? So M1, M2. Now we have derived or we have measured certain values for them. We have measured their R squared, we have measured their adjusted R squared, we have measured their AIC, and we have measured their BIC. Okay, let's plug in the values here. Let's say M1 has a R squared of 0.8 and M2 has an R squared of 0.85. M1 has an adjusted R squared of 0.75. M2 has an adjusted R square of 0.88. Now, M1 has an AIC value of 25.3. M2 has an AIC value of 21.3. M1 has a BIC value of 22.7. M2 has a BIC value of 20.1. Now we have a few questions to answer from this problem. This is our, let's say this is our data set, and we will solve a few questions and answers from this. The first question is, does model 1 or M1 has a t-statistic value of greater than 1 in magnitude or less than 1 in magnitude? Is the magnitude of t-statistics for M1 greater than 1 or less than 1? The answer is t-stat is greater than 1. T-stat magnitude is greater than 1. Why do we say so? Because you see, in this model, there are two variables, a1x1, a2x2. Here, you have added one more variable, a3x3. And you see the adjusted R square has increased in model 2. It was 0.75, it has become 0.88. So this means the magnitude of t-statistics has to be greater than 1, because in that case only addition of a variable leads to increase in the adjusted R square value. This is question number 1. Question number 2. Which model would you use for predictive purpose? The answer is for predictive purpose, we have to see which one has a lesser AIC or a key keys information criterion. So among these two, model 2 has a lesser AIC. So the answer is model 2. Question number 3. Which model would you use for judging goodness of fit? Which one should you use, guys? The answer is the model with the lesser BIC. So here the lesser BIC, this lesser BIC is also for model 2, M2. So here also the answer is M2 or model 2. Right? So these were a few sets of problems that we solved just to revise what we have studied. Now we'll move to the next section,